After completion of this section, the student shall be able to identify and describe possible problems related to the fuel injection system. Have a pleasant learning lesson. The low-speed two-stroke diesel engines are dominant in marine propulsion and are expected to remain so in the foreseeable future. As the fuel injection system is the heart of the diesel engine, it is of vital importance to understand and maintain the performance of the system. This lesson will guide you through some of the aspects regarding fuel injection, atomization, and combustion. Looking at the rotation of the crankshaft, it is common to use two positions as reference. These are top dead center, TDC. This is the situation when the piston is at the top position and the movement of the crank is altered from an upward to a downward direction. Bottom dead center, BDC. This is the situation when the piston is at the bottom position and the movement of the crank is altered from a downward to an upward direction. The two-stroke principles can in broad terms be divided into 4 stages. As can be seen, we have the sequence scavenging, compression, combustion, expansion. On its way upwards, the piston will first provide that the scavenging ports in the cylinder wall will be closed, and approximately at the same time, or a little bit later, the hydraulic system will provide closing of the exhaust valve. At that time, the compression starts, and as the piston moves further upwards, the pressure and temperature in the cylinder will increase. The mixing of fuel and air in diesel engines does not take place until shortly before the end of compression. The fuel oil is sprayed into the highly compressed hot air, where it ignites due to heat produced by compression without the use of any ignition mechanism. Before ignition, the fuel must be atomized to a mist and distributed as quickly as possible throughout the whole of the compression chamber. When the mixing of fuel and air has reached a certain suitable mixture, the ignition will take place, leading to the combustion process. This results in a certain increase in cylinder pressure, and the temperature in the cylinder mixture will increase to values in the order of 2000 Kelvin or so. 1 degree Kelvin is equal to minus 273 degrees centigrade. The combustion process may be divided into 4 stages, and will be more thoroughly explained later in this lesson. The pressure increase developed in the cylinder by the combustion will force the piston downward. The exhaust valve will open, and the exhaust gases will be expelled by their own kinetic energy into the exhaust gas receiver. Thereafter, when the scavenging ports are uncovered, the scavenging air flushes the remaining combustion products out of the cylinder through the valve opening. This expulsion of the exhaust gas is sometimes referred to as exhaust blowdown. Each fuel pump feeds the injectors fitted to one cylinder. The fuel is introduced into the combustion chamber through 2 or 3 nozzles with a large pressure difference between the fuel supply line and the cylinder. MAN, B&W MC90 engines have, for instance, an opening pressure of the injectors of about 420 bars and a maximum injection pressure of about 700 bars. The fuel pumps for larger diesel engines incorporate variable injection timing for optimizing the fuel economy at part load. The start of the fuel injection is controlled by altering the pump barrel position by means of a toothed rack. Individual adjustment can be made on each cylinder, and collective adjustment of the maximum pressure level of the engine, also symbolized as P max, can be carried out to compensate for varying fuel ignition qualities, wear, etc. The upper rack is for adjusting the variable injection timing. The lower rack is for adjusting the amount of fuel. It is mandatory that both the fuel pump and the injectors are kept in good condition. Neglecting adjustments and poor maintenance may lead to poor combustion. The exhaust valve situated in the center of the cylinder cover of each cylinder makes it necessary to use 2 or 3 injectors per cylinder in order to achieve an optimal spray pattern. Three injection valves give the advantage of a more uniform temperature distribution around the main combustion space components, cylinder cover, cylinder liner, and piston crown, at the increased maximum combustion pressures, together with even lower temperatures in spite of the higher loads. It also gives significantly lower exhaust valve and valve seat temperatures. The illustration shows the spray pattern from 3 injection nozzles. Looking at the fuel pump, we recognize that the cam on the camshaft will force the fuel pump plunger upward during rotation. The pressure wave between the pump and the injector will move at a supersonic speed of 1300 to 1500 meters per second. When the wave hits the injection valves, part of the fuel mass will be reflected back through the pipe like an echo. Reflecting pressure waves in the fuel line may lead to uncontrolled opening of the fuel valves, which normally will lead to dripping from the valves. The results will be afterburning and build-up of carbon at the nozzle tip, which in turn may lead to distortion of the spray pattern. To avoid such situations, a suction valve is mounted in the fuel pump. When the reflected wave returns to the pump, the suction valve will close. The small movement of this element will increase the total volume of the pipeline just enough to reduce the pressure, thus avoiding an additional opening of the injection valves. In order to achieve an optimal spray pattern and a good atomization of the fuel, the valves must be adjusted to correct opening pressure and maintained according to manufacturer instructions. The real spray pattern is more complex, as the turbulence and swirl of the air will have a great influence. As the liquid jet leaves the nozzles, it becomes turbulent and spreads out as it entrains and mixes with the surrounding air. The liquid column leaving the nozzles disintegrates within the cylinder over a finite length, called the breakup length, into drops of different sizes. Close to the nozzle tip, the outer surface of the jet breaks up into drops of about 10 mm in diameter. As one moves away from the nozzles, the mass of air within the spray pattern increases, the spray diverges, its width increases, and the velocity decreases. The fuel drops evaporate as this air entrainment process proceeds. The tip of the spray penetrates further into the combustion chamber as injection proceeds, but at a decreased rate. The droplets on the outer edge of the spray will evaporate first, creating a fuel vapor air mixture sheath around the liquid-containing core. The highest velocities are on the jet axis. The equivalence ratio is highest on the center line and fuel-rich along most of the jet, decreasing to 0, unmixed air, at the spray boundary. To couple the spray development process with the ignition phase of the combustion, it is important to know which regions of the spray contain the fuel injected at the beginning of the injection process. These regions of the sprays are likely to ignite first. Each spray develops as follows. At the start of injection, the liquid fuel enters the quiescent air charge, atomizes, moves outward from the nozzles, and slows down rapidly as air is entrained into the spray and accelerated. This startup process forms a vortex, or puff, at the head of the spray. The injected fuel which follows encounters less resistance. Thus, drops from that fuel overtake the drops from first injected fuel, forcing them outward towards the periphery of the spray. At the tip of the unsteady spray, the drops meet the highest aerodynamic resistance and slow down. But the spray continues to penetrate the air charge as droplets retarded at the tip are continually replaced by new, higher momentum, later injected drops. Accordingly, droplets in the periphery of the spray and behind the spray come from the earliest injected fuel, and these drops evaporate quickly. Both physical and chemical processes take place during the ignition delay. The chemical properties of the fuel are much the more important. The ignition quality of the fuel, defined by its cetane number, normally not used when evaluating HFO, will obviously affect the delay. Straight-chain paraffin compounds, normal alkenes, have the highest quality, which improves as the chain length increases. Aromatic compounds have poor ignition quality, as do the alcohols. Because residual fuels are blends of many different compounds, there has so far been no standard test method for evaluating their ignition quality. Today, the most common measure is the CCAI evaluation developed by Shell. Calculated Carbon Aromatic Index, CCAI, is only based on the density-viscosity relation and does not allow a complete, accurate prediction of ignition quality. The physical factors that affect the development of the fuel spray and the air charge state, its pressure, temperature and velocity, will influence the ignition delay. These quantities depend on the design of the fuel injection system and combustion chamber, and the engine operating conditions. The injection system variables affecting the fuel spray development are injection timing, quality, velocity, rate, drop size, spray form or type.